And why all particles develop charge on their surface in aqueous solution? There are different ways. One is so-called preferential ion adsorption from electrolyte solution. Okay, the water aqueous solution, but there are charged species within the water, within your solvent, essentially. And your particle, because your nature, your chemistry nature, preferential absorb certain ion, positive or could be negative, and then that would lead to the particle surface to be covered by certain charge. For example, if the particle likes proton, then it would selectively or preferentially absorb protons onto the surface. Or if it likes hydroxy group negatively, then it would selectively attract hydroxy groups from the water. And it, other than this proton hydroxy group, it may also absorb other charged ions from, quite often, electrolyte solution, from salt solution, or from acid or base solution. Okay. Even for neutral, we may have so-called non-stoichiometric dissolution. My particles, okay, will always have some solubility within the suspension, within the solvent. Okay. You think any material would have some solubility, except in some cases solubility is pretty low. But in some cases, it's so-called non-stoichiometric. Preferably, certain ion dissolves out, certain ions keep on the surface, and as a result, the particle surface will also be charged. We'll talk about that. And another possibility is adsorption of charged polymers or polyelectride, which is kind of an steric effect. Okay, let's first talk about surface charge development through what? Preferential or selective ion adsorption from solution. The first one we are looking at is preferred adsorption of either proton or hydroxy group. Okay, and for these, the oxide surface quite often, they have surface groups such as OH, which preferentially absorb either the proton or hydroxy group and determine the surface potential and charge on the surface. The ions such as different cation, barium, aluminum, silicon, titanium, zirconium. For these types of cations, the process, we may have something like this. The surface of your metal oxide, the surface initially terminated by a kind of a neutral OH group, and then when we dissolve them in a solution that contains proton, then the proton got attached onto this OH group, and the surface now become positively charged because the proton attached here. Okay. Or in some cases, the surface covered by initially neutral OH group, but then the suspension contains certain things that attracts away proton, then I'm having a negative charge, MO. Make sense? Neutral, but then preferentially dissolve, let the proton go away, then becomes MO minus. Or MO, but then there are hydroxy group, there are base group in the suspension. I got MO, but then form a water. Kind of these two are essentially equivalent. One is producing proton. The other one is consuming hydroxy group. Make sense? When you consume hydroxyl group, the net effect is essentially, if it's thinking of charge balance, we are creating proton. They're kind of equivalent. These two are kind of equivalent. Different ways to write it. An example is the edge of clay particles, for example. Clay particle, quite often, they have aluminum OH group attached. And then when we dissolve them into water, we would have positive aluminum and hydroxy group dissolved in it. Okay. The other one, and let's continue a little bit, surface charge. Apart from this proton or hydroxy group, there are other ions that may also selectively or preferentially absorb onto the ceramic particle surface and become the potential or charge determining ions. Here we give one example, the citrate ion selectively absorb onto the aluminum oxide surface. Okay. Here, if we citrate ion, where does it come from? We dissolve sodium citrate in as an electrolyte and into the solution. Sodium would be the so-called counter ion. The citrate ion is formed. Okay. And if the initial our aluminum oxide surface is neutral, and the preferential absorption of the citrate ion, which is, if sodium is positive, the citrate ion should be what? Sodium is positive, the sodium citrate should be negative. And if it's initially neutral, citrate ion absorption, selective absorption onto the surface would lead to negative citrate ion absorbed onto aluminum oxide. It leads to negatively charged surface. So this kind of like aluminum oxide initially neutral. We put that add sodium citrate into it. And citrate ion, this negatively charged citrate ion selectively attached to the aluminum oxide surface. And as a result, this particle become what? Negatively charged, while the solution has slightly actual sodium ion in it. Okay? Okay, so let's continue a little bit. This one we are going to talk about non-stoichiometric or preferential dissolution. This can also give us what we want, which is particles with surface charge. Okay, so in this case, certain solid they are going to experience non-stoichiometric, which means okay, they have, put it the other way, they have preferred dissolution of certain ions from the particles and leaves certain other ions, also called counter ions, on the surface, which gives it the surface charge. And one example is silver iodide. Ag for silver, I for iodine. Silver iodide in water. And the silver iodide may go through non-stoichiometric dissolution in aqueous solution, depending on the solution, how much of a silver ion or iodine ion in the solution. And the people observe, for example, when the solution contains too little what? Silver ion. When the solution contains too little silver ion or too much iodine ion, then what would happen is, okay, the solution is have too little silver. So if you are going to guess, we would have preferred what? Dissolution of which ion? The solution has too little ion. So quite often what would happen is we would have excess dissolution of silver. The solution is in need of silver. So the particle have give it more silver and lead into the surface with excess iodine and become negatively charged, something like this. something like this. If the outside solution has too little silver, and as a result, to compensate, this silver iodide has give out a lot of silver into the solution, and as a result, the surface would be richer in iodine, and richer in iodine, the surface closely would be negatively charged. Okay, so this is one example of so-called preferential dissolution. The other one would be the solution contains too little. The other case contains too little iodine, and in this case, we would have excess dissolution of iodine, and leading to excess silver ion on the particle surface, which is positively charged. Okay, the graph here is for the surface to be covered by excess iodine, negatively charged. And the dissolved silver go into the solution to compensate, okay, for the deficiency of too little silver in the solution. And another types that we are going to talk about a little is so-called isomorphic substitution. Isomorphic substitution. So typically it happens for when the high valence cation is replaced by low valence cation in the ceramic material like aluminum or silicon replaced by magnesium. High valence cation replaced by low valence cation. And it would quite often lead to extra cation adsorbed on the surface to compensate, to achieve so-called charge balance, especially for so-called clay particles. In this case, one example would be silicon ion in the ceramic got replaced by aluminum ion, but silicon ion has valence plus 4, aluminum has valence plus 3, so it's not a neutral one. For charge compensate, quite often this clay would have surface be attached to some so-called sodium ion, positive, so that I have 3 plus and 1 plus, together I have 4 plus. I achieve so-called charge neutrality. Another example, aluminum cation 3 plus replaced similarly by magnesium, but then it's not charge balanced, so the surface got attached with a so-called sodium ion. This is type of so-called isomorphic substitution. Silicon replaced or substituted by aluminum, aluminum substituted by magnesium, but then I need some surface cation to compensate. So this is what it roughly looks like. A clay particle, okay, initially with sodium attached on the surface. Why sodium attached on the surface? Because within the clay, there are some of the high valence cation replaced by low valence cation. Okay, and then when we put this clay particle into the water, naturally what happens would be the sodium got dissolved away. The attached surface cation got dissolved away. Upon dissolution in water, the cation attached at the surface, they dissolve and leave the surface become negatively charged. As this attached sodium leave the surface is left with what? Negative charges. Okay? An example would be this one. Example would be this one. It's not a exact reaction per se. It's a kind of a like substitution. Aluminum, initially I have 2 aluminum here. Now aluminum replaced by aluminum plus what? Magnesium. That's the replacement. But because magnesium has lower valence state compared with aluminum, so the surface in its formation has a lot of attached sodium. But this sodium is excess. It's not into the lattice. It's only at the surface. And when you dissolve this whole clay into the water, this sodium would so-called would leave, would dissolve, and the the remaining clay particle would be what? Negatively charged. Negatively charged. This whole thing before dissolution is neutral, but when you put this whole thing into the water, the sodium, small ion, dissolved. Water like sodium, so the sodium dissolved, and whatever the remaining part would be negatively charged. And if each of them are negatively charged, they would develop repulsive force between each other and become stable. Okay, that's for clay particles.